Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, collisions part 2. Now we're going to talk about elastic collisions. Now, an elastic collision has two important things in common. We talked about this in the last video, but it's important to understand that two things are conserved. Conserved, momentum and kinetic energy are both conserved. So essentially we're going to say mv, and this is vectorial, is equal to mv. But also ke is equal to ke from initial conditions and final conditions. And we can do some really cool problems with this that teach us some super duper awesome stuff. And before we do an example, let's just talk about, again, what kinds of things are elastic, like super bouncy balls. We talked about molecules in the air, or Newton's cradle can also be considered a elastic collisions. And some collisions tend to be really elastic. To do this, we need to do a relatively long problem. So get your calculators out, follow along carefully. As you do this problem, you need lots of space. Take careful notes as I go through the steps to solve this problem. I don't know about you, but I'm fascinated by the sport of curling. I don't know, it just seems fun and it's cheesy and weird. Let's do a curling problem. So in this problem, we have a 16 kilogram stone. And it's moving at 1.5 meters per second. And it's going to be an elastic collision with another stone that then takes off at 0.69 meters per second. The question is, what is his mass? You'd like to say mv equals mv, and yeah, no. Yeah, it's not going to work on this problem. So let's do it. So we're going to say m1v1 equals m1v1 plus m2v2. Now I could actually say m1v1 plus m2v2, but since this is at rest, the m2v2 is 0. These are the prime or the second conditions. So let's plug in some numbers. We know that this is 16 times 1.5. And that's going to be equal to, now what's the m1? 16, but I do not know his velocity. What is his final velocity after the elastic collision? So that's v1. Plus, I don't know his mass, but I do know his velocity to be 0.69. Make sense? Let's simplify that. If I simplify this, 16 times 1.5, that's 24, equals, I'm going to just 16v plus 0.69m. I'm trying to put it more algebraic. So this is one equation, but you might notice you can't solve it because you have two variables with two unknowns. All right. Remember, in an elastic collision, something else is happening as well. What's happening is kinetic energy is also conserved. So I can say 1/2 mv squared equals 1/2 m1v squared plus 1/2 m2v squared, and I'll say prime, the final velocity. But we can plug in some numbers. I know the initial mass, so that'd be 1/2 times the mass, which is 16, times the velocity, 1.5 squared. I'm plugging in the numbers that I know. This will be 1/2 times 16, this is the stone number 1, times, we don't know this, v, I'm just going to call this v squared because there's only one v down here. It's actually v2, whatever, plus 1/2 times m, I don't know that, but I do know this, which is 0.69 squared. Now that's a lot of numbers. Let's simplify those numbers. When you take this 1/2, all this whole term becomes 18. All right, and I can say 18 equals half of 16. That's 8v squared plus half of don't forget to square the 0.69 squared. And I get this whole term to be 0.238 times m. So half of 0.69 squared. So now I have a second equation. Now, you math hacks, this is where we can solve this problem. We can solve for m and we can solve for v. Now I'll show you how I did it for what it's worth, because we want to find m and v. That's what they're asking for. What's the final velocity of this guy, the initial stone, so V equals question mark, and what's the final mass of this one. And so the way I set this up is I solve for M from this equation here, right? So if I subtract, so 18 minus 8V squared, I'm subtracting 8V squared equals 0.238 M. And if I divide both sides by 0.238 and 0.238 M, this equals M, this whole term, right? But now if I know that's M, what can I do? I can plug that in to this equation, so I can now say 24 equals 16V plus 0.69 times this big term, 18 minus 8V squared over 0.238. Now, at this point, Mr. Bergmann, this is a quadratic formula problem. We got a V squared, we got a V, and we got a regular number. I hate doing quadratic formulas. I plug this into my solver, and I got an answer. And as a note, I got a negative answer. I got the velocity, and this makes sense if you think it, to be negative 0.81 meters per second. Because when the stone hits the other stone, he bounces back and moves with a negative velocity, which makes sense. It'll make actually more sense if we then figure out what the mass is. So so if we know this V, we can now plug this into this equation, because we now know it's negative 0.81, and we can solve for the mass. So this would be equal to 18 times, minus, pardon me, 8 times negative 0.81 squared divided by 0.238, and I get a mass equal to 53.5 kilograms. Now, let's talk about that. Does that make sense? Because this is a negative. As the first stone comes and hits, he bounces back. He only weighed 16. He hit a really massive stone, a 54 or whatever kilogram stone. So he bounces back, and this guy creeps along at about half the speed, and he bounces back at a faster speed. The key to this, folks, is understanding that kinetic energy is conserved, momentum is conserved, two equations, solve for each, and then we don't have a problem. Now, is this a nasty problem? Does this have a lot of steps and a lot of numbers? This looks confusing. And I didn't even show you how I did the quadratic formulas. So this is going to take a lot of time when you're doing these in class, but this is the big idea. When you have an elastic collision, you have two equations, you set them up. It's important to figure out who is which and what number you're solving for. You'll solve for the M and the V, and Houston, we won't have any problems, because you're going to figure out how to do this in class, because, well, you guys are awesome. Because, yeah, I know you are, because you're my students. You are amazing. We'll see you in class.